Okay, no problem. So thank you all for coming to our IVEM seminar series. This is the last seminar in our previous calendar. And so we'll break for the summer and then restart again in the fall. We'll be sure to send you the information with that. But today I'm happy to welcome you to a talk by a former colleague of mine, Lukas Woodcock. He did his bachelor studies at Ferris State in Michigan, where he worked on his tag removal and heme incorporation in recombinant CCP1 proteins and some other biochemistry related stuff. He got his bachelor's in biochemistry there and then went on to pursue a PhD in the Eaton group, studying rapid scan and other EPR techniques, which most of you will probably be familiar with the work from their group. And today he's going to talk to us about his work developing a 1 GHz benchtop EPR imaging system. So without further ado, I will hand it over to Lukas and take it away.
All right, well, thank you for that introduction. As you said, I've been working in the Eaton lab, and I'm going to talk to you today about the work we've been doing developing and modifying this EPR imaging system. Before I get started, I'd like to make some quick acknowledgements. First off, current and former members of the Eaton lab. Of course, my PIs, Drs. Gareth and Sandra Eaton, Joe McPeak, who has been quite helpful in helping me learn how to measure noise, which you don't really think you need help on, but Dr. Laurie Buchanan, who did the early work on the instrument, Kit Canny, who's been helping with data workup and programming, Sam DeGraw, who helped with both data workup programming and a little bit on the instrument design side of things, and Tandon Hovey, who's currently helping me quite a bit with instrument design. And then, of course, our engineers, Dr. George Reinhardt and Richard Quine, the latter of whom actually designed the initial instrument. And then, of course, the NIH for keeping the magnets on. So an overview of what we're going to talk about today. First, I'm going to give just a brief introduction into some imaging concepts, going over field gradients and imaging probes. Then I'm going to jump right into talking about the design changes we've made on the EPR imager, which is going to include a simplified design and selection of a newer source. So to briefly talk about EPR, I'm sure most are familiar with the lovely energy splitting diagram. One of the things I wanted to expand on with this in relation to imaging is the field frequency relationship. Most people are probably using X-band for most of the work they do on EPR. For imaging, you can't really use X-band. The penetration depth is quite literally only skin deep. So we have to go to lower frequency. We chose to utilize 1 GHz for our frequency as it affords some benefits. First, the signal to noise and penetration depth trade-off is just about ideal at 1 GHz for a preclinical imager if you're planning on measuring things such as mice. Additionally, because we're only producing a field of about 38 millitesla, we don't have to water cool the magnet, and we can have the magnet be air core, which sort of lowers the engineering burden on designing the magnet and power supply systems. So beyond this, of course, we know we can add nuclear hyperfine to get more information about the electron surrounding environment. Moving on from the basics of EPR, we need to talk about how we actually take the image. So the focus of that is going to be on what are called field gradients. So when you create a normal field, you have a Helmholtz coil pair. And in this diagram, we have the electric fields in the white vertical arrows, the individual magnetic field as the blue circular arrows, and then the net field is red. And when you use a Helmholtz pair, the result is a homogeneous field in space. So at every point in space, the field is going to be the same value. To create a field gradient, literally all we do is flip one of those coils around to create an anti-Helmholtz pair. And the net result is right at the center of these two coils, the fields cancel out. So we have no additional field at that point. And as we move out from the center, the fields gradually get stronger and stronger. Graphically, what this looks like is a predictable change in field as a function of space. So with no gradient field, we have no spatial information encoded. And then as we increase the strength of the gradient field, we increase the slope of the relationship between distance and field offset. So unlike other imaging forms, primarily MRI, which has an abundance of signal to work with in an in vivo body in the form of water mostly. If you know anything about biochemistry, you know that it doesn't like leaving unpaired electrons around. So there's not a lot of signal for EPR spectroscopists to draw off of in just a native in vivo setting. So we have to add imaging probes. The most common moiety for imaging probes is the so-called nitroxide. Pictured here, I've got carboxyproxyl, which produces a 3-line spectrum as pictured below. This sort of probe is useful for gaining a pretty wide array of information. Probes have been designed to get pH information, redox information, less commonly oximetry. Of course, nitroxide aren't the only probes available. There's also the Trittle probe. Pictured here is Trittle OX63, which produces the very sharp 1-line spectrum from the carbon-centered radical. The most common usage of nitroxide probes in imaging has been for oximetry. So that's the short version of imaging and what we really need to know for the talk going ahead. So let's jump right into talking about the instrument from here. First, let's go over what the instrument actually looks like. I'm sure some of the components here are familiar. On the desk here, we've got the magnet and resonator system. Loaded into the magnet is a cross-loop resonator. This red ring around the center is the face of the rapid scan coils. And then, of course, we've got our very high-tech cooling system. We've got down here at the bottom 4 bimodal power supplies that are controlling the main magnet and gradient fields. They allow us to create both positive and negative fields. We have the computer here, which contains the control software as well. It's loaded with a PCIe digitizer. We have the bridge, which contains all the RF components, tuning circuitry, and detection system. We have Tektronix AWG in this configuration, which is only utilized for producing a tuning chirp. The Roden-Schwartz source, which has been selected, providing the RF to the bridge, and then the rapid scan coil driver. So the aims of this project were to increase the signal to noise. We did that by a number of ways. First, we primarily looked at bridge modifications. We converted the bridge to exclusively run rapid scan, which allowed us to remove some extraneous components. We replaced the circulator with a directional coupler as the directional component. We'll go into detail on all of this in a little bit. We moved the first stage amplifier closer to the resonator, and we selected an improved source. We're not going to talk about it in this talk, but it's worthwhile to mention we also spent quite a bit of time working with our engineer, Dr. Reinard, who designs all of our resonators, on testing those and seeing how much signal to noise improvement we could get through that avenue. So let's start by giving a reference point for where the bridge started when it was handed to me. So this is the design as published in paper by Buchanan. There's a lot going on here, so I want to draw your attention to a few different things. First, all the currently highlighted components are specifically for operating the bridge in a pulse mode. And so when you run it in rapid scan, it does little more than add insertion loss. Second, we have 8 tuning components, 4 of which are in the detection path, which we looked towards simplifying. As I said earlier, we switched a circulator over to a directional coupler. This is where we have it located. It's actually located outside of the bridge in our design. And then here is our first stage amplifier. And obviously this diagram isn't to scale, but there's quite a bit of cabling and several components prior to it, which increases the noise of the system. So we made a bunch of changes to the system, and the result of that looks something like this. It's much simpler, but there's still quite a bit going on. First and foremost, there are no pulse components to highlight here. As far as tuning goes, we've dropped the components from 8 to 4, with similarly only 2 of them now in the detection path, so greatly reducing the loss from these components. We have switched over to a directional coupler, and our first stage amplifier now resides outside of the bridge as close to the resonator as we can get it, with now only about a foot of cable and those 2 components there preceding it. So how do we tell that all these changes have made any difference? Well, we do that with a value called the noise figure. Basically, this is a value usually listed in dB that describes just the noise of the system. We have 2 ways of measuring that. One, a theoretical calculation based on component performance. This is the Freeze equation, or Freeze cascading amplifier equation, as it's sometimes called. And it looks something like this. So the noise of the system is a sum of the noise of the everything before the first stage amplifier, and then and then following that, the noise of the first stage amplifier over the gain of the first stage amplifier, the noise of the second path over the gain of the amplifier and path before it, and so on and so forth. What this is able to tell us is first about what trade-offs we can expect with adding gain at specific areas. Specifically, if we are able to increase the gain at, say, the first stage amplifier, it lets us know how much we can expect to drop the noise of the system. But as a further trade-off of something like that, because of limitations on hardware, we know as we increase gain in earlier areas of the instrument, we have to limit how much gain we can put elsewhere. So this sort of informs the design that way. We can also directly measure the system's noise using the so-called Y factor method. When we look at the Y factor method, there are 4 values we need to consider. First is the power input to the system in a cold state. This is basically just the thermal noise of the system at room temperature. And then the power input to the system in a hot state, which is thermal noise plus a noise input from a calibrated noise source. Both of these values are calculated values. And then we have the power output of the system in a cold state, which is the measured output with no CNS input. And then the power output in a hot state, which is the measured output with the CNS input. So as far as an experimental setup goes, the calibrated noise source, is put in place of the reflection resonator, and then we measure the output at one of the digitizer output channels. So as far as comparing the old system to the new system, as published, the old bridge design had a Y factor value of 11.2 and a calculated freeze equation value of 9.9. With the new system setup, we have a Y factor value of about 6 dB and freeze equation calculation of about 6.5. So they're in good agreement, and we've cut the noise of the system almost by half by making the alterations we've made. As I've mentioned a couple times, we investigated switching the directional coupler with a circulator. Now, in a typical bridge, the circulator acts as a sort of like a traffic circle for the RF in the system, where we have power exiting the bridge and entering into the circulator, where it travels on to its second port, heads down to the resonator where the signal is generated. The signal is reflected back out into the circulator where it heads on to port 3, and the signal heads on into the bridge. We realized that if we installed it backwards, we could utilize a directional coupler to do the same job and potentially get a better signal to noise from it. A directional coupler is basically just a specialized cable with an antenna. It's not quite a cable, but it's just a transmission line, with an antenna that only picks up RF flowing in one of the 2 directions. So to utilize it sort of backwards, we output our signal as usual, but we input it into the coupled port of the directional coupler and utilize its directionality to have that sent towards the resonator, where once again the signal is generated and then reflected back out and sent to the bridge for detection. So in comparing these two, the value that we're most interested in is called directivity. Basically what this is just the amount of RF that passes retrograde to the expected flow of RF. So for the circulator, that's as expected 1 to 2 to 3, and for the directional coupler as we're using it is from the coupled port to the input port. And the directivity describes all of the flow that's passing in the retrograde direction. So anything going from 1 to 3 or 3 to 2, and anything going from the coupled port to the output port. The reason this is important is that any RF power that's passing this way is basically bypassing the isolation of the resonator and sort of limiting what we can amplify with our first stage amplifier. So we can measure this value directly, or we can measure the signal to noise of a signal utilizing both configurations. So what does that look like? Well, when we measure it directly, the directivity value for the circulator comes out at about 20 dB, and the directional coupler comes out at about 35 dB. So this tells us that the directional coupler does seem to have a bit better directivity. However, the real telling measurement is, of course, the signal to noise. Here we measured Triddle OX63 as I believe I showed a structure of that earlier. And when we compare the signal generated with the same B1, the signal to noise of the circulator shows about 420. The signal to noise of the directional coupler about 530. So we're getting about a 20% increase in signal to noise, which is pretty good. So we elected to continue the rest of the tests with the directional coupler. As I also mentioned, we investigated a bunch of different RF sources, and for EPR, the primary concern is a value known as phase noise, and this value is basically just instability in the RF phase. It's also sometimes referred to as frequency jitter. How we measure this value is by detecting our signal in quadrature, and then we can utilize the signal to properly phase the RF such that one channel possesses only absorption information and one channel only possesses dispersion information. And the channel that possesses dispersion information is also going to contain our phase noise. And we can measure the noise as a function of power to see when phase noise begins to dominate over the thermal noise of the system. We tested several sources, and what that ends up looking like is something like this. So we have our absorption channel here, which tells us information about amplitude noise, and we have our dispersion channel here, which tells us our phase noise. And right away, you might notice that the Roden-Schwarz source that we're currently utilizing has exceptional phase noise compared to the other sources that we tested. The Holtzworth and microlambda source are fairly comparable with pretty good phase noise and amplitude noise that's on par with the Roden-Schwarz. The Tektronix AWG, being an AWG, suffers from worse phase noise than the other analog sources, and this is due to the digital nature of AWGs being dependent on having frequencies that are some multiple of their fundamental time base, causes a little bit more phase noise when you're selecting frequencies that aren't multiples of that time base. The BNC source is another analog source that actually does have slightly better phase noise than either the Holtzworth or microlambda. However, we found that it suffered from quite a bit of amplitude noise as well. And then the SP Teledyne is a PCIe mounted AWG that suffers from some severe phase noise problems. So we elected to continue on with the Roden-Schwarz, as we were looking for signal to noise, and it has the lowest noise profile of the system. So we've made all these changes, but what does that look like in terms of the EPR? One of the ways we tested that was trying to push our limit of detection as far as we could go, and we did that with a 15N isotopically purified Tempol sample. Spectrally, that looks something like this. I've got the structure as an inset here, and for anyone who's seen a EPR spectrum, this might not look too impressive. However, this is a sample that's very dilute with only 2 × 10⁻14 spins for a more familiar unit that's about 1 micromolar in an 8 millimeter tube. This is also only a 10-second collection, but utilizing rapid scan, 10 seconds means 200,000 averages. So for L band at such a low concentration, this is really pushing it. This is pushing things in the right direction. This is definitely something that's beneficial for when we try to take magnetically dilute images. Speaking of images, we tested the imaging with a 0.4 millimolar CTPO sample. The phantom for that looks something like this. Again, I have a structural inset here for the sample. Our phantom is on a surface coil, so we're taking the image along the y-axis. The total size of our phantom here is 5 millimeters with a 4.2 millimeter spacing center to center from the two samples. These are just loaded into glass, thin glass tubes with a couple empty ones in between to give us some spacing. So we take the image, reconstruct it, and that ends up looking something like this. So the image that you're looking at here is two-dimensional spectral spatial. So we have the image in the y direction here. So you can imagine along the zero line here is the surface of our surface coil. And then along this dimension here, we're looking at the field axis. So at each point in space here is a different spectrum. And so what we could do with this sort of image is we can pick a point, let's say at about half millimeter up, and extract the spectral information from that. And that tells us a little about what spectral information is going on at that position. So we can extract that, and it ends up looking something like this, which tells us about the line shape and environment of that area. So that's some of the progress we've made. Looking forward, we are looking at improving some of our software and adding some additional functions to what we can currently do with the system. This includes 4-dimensional imaging, so 3 spatial, 1 spectral dimension. Basically what I showed you, but with more information about the spatial distribution of the signals. We've looked into adding a so-called rotating gradient scheme. Basically, the current way we take images is we set the gradient field at a specific value, take an image, set it at another value, take an image, or take a spectrum, set it at another value, take a spectrum. A rotating gradient scheme sort of allows the whole system to flow through all the points in a very tightly timed scheme. We're also looking at packaging the control software in a standalone program. Currently, it's inside MATLAB. And not everybody has a MATLAB license, so we're trying to separate that out. We've also looked a lot at further characterizing the rapid scan background. As anybody who's utilized rapid scan will tell you, one of the sort of more pernicious problems with it is dealing with a sinusoidal background that it creates. Part of the project moving forward is also going to be constructing a bridge to do just pulse experiments. And then finally, we've been working quite a bit with the Noisig lab, who is out of CU Anschutz, and they've been modeling lung disease in mice, and we've been taking some images for them. So yeah, that's what we've been doing. I'm happy to open the floor for questions, and thank you all for your attention.
Yeah, thank you for that nice talk, Luke. Yeah, so if anyone has questions, we're a pretty small group today. You can just turn on your camera or microphone and ask, or send in the chat and I'll read it. While we wait for other people to formulate their questions. I had a question actually concerning how you're using the Roden-Schwarz source.
Mhm.
So you were comparing different phase and amplitude noise of your microwave sources, but some of them were digitally programmable and some of them weren't. Can you maybe
Yeah.
speak a bit on how you're using it and what the benefits and drawbacks there are?
Can you clarify what you mean by how we're using it?
Yeah, sure. So are you, the question on my mind is, are you mixing one of the analog sources with something more programmable to preserve the flexibility, or are you just completely sacrificing the programmability to achieve the low phase noise that you show in the Roden-Schwarz source?
We're doing the latter. We're completely sacrificing flexibility. That was sort of the for lack of a better word, the point of sort of simplifying the system down to only running rapid scan. We've sacrificed all the flexibility that was initially published, because the initial bridge was designed to do it all, right? It was able to do pulse, it was able to do even saturation recovery and rapid scan. And they were utilizing the Tektronix AWG, which is a very advanced AWG, and is able to do both continuous wave and designed pulse shapes, but it came at obviously came at the expense of signal to noise. So we basically just scrapped the idea of being able to have a bridge, one bridge to rule them all, and instead just focused on how far down can we push the limit of detection, how much can we increase the signal to noise.
Okay, so it's basically, so you're basically just using a continuous wave source then. Or using the source as a continuous wave source. Do I understand that correctly?
Yes, we're just using it as a continuous wave source. Yep.
Okay.
Looks like there's a chat.
Yeah. Will asks, how does the detection work? Is there a delay line?
No, there's not. So we're utilizing a quadrature detector. Let me go back to the bridge diagram one moment. So where is that? That is here. Right. So let me turn the highlights off. So we're this is our detector here. There's no delay line. If I understand what you're asking, excuse me, sorry. If I understand what you're asking, you're probably wondering why there's not a phase shifter of some kind on the LO side, the reference side of the system. The reason being is even on systems where we do have some kind of phase control of the RF, we inevitably have to adjust the phase in post. So to simplify the internals of the bridge and frankly give me more room to work, I just took out the phase shifter and we do all the phase shifting in post. Surprisingly, the Roden-Schwarz being very low phase noise and the system being as compact as it is, surprisingly most of the spectra I take are really close to properly phased anyway, which it was kind of a surprise to me. I expected it to just be a random spot and just stick there, but yeah, we're not utilizing any sort of delay line or phase shifting, and we're just utilizing a 0-degree splitter and a hybrid splitter with 2 mixers as the detector. Does that answer the question?
We'll see in the chat in a moment. I want to maybe piggyback off that a little bit. So I said thanks.
Yep.
So you're not using a phase shifter, and so you can manipulate the signal phase in post-processing, but that is, in my understanding, primarily determined by the phase of the reference. Do you notice, or have you done the experiment where you put a phase shifter in the reference arm and see how your noise level or noise spectral density changes over the full 360 degrees without respect to your signal phase?
I have not done it over the full 360 degrees, but I have put it in to see how much it changes the noise, and it doesn't seem to affect it terribly much.
Okay, that's good.
Which was a surprise to me, and we have discussed about that previously. So
Yeah,
Okay. Can I ask a question?
of course.
Sure.
Yeah. What is the maximum gradient you can go with your imaging system?
let me see, in the Z direction, so the Z coils are a little more powerful than the X and Y coils, but in the Z direction we are able to get, I believe, up to 1.5 millitesla per centimeter, and in the X and Y direction I believe they only go up to about 1 millitesla per centimeter.
Okay. My next question is, what is the maximum scan width you can go with your rabbit scan?
That's quite a question. So that depends on a lot of things. First, it kind of depends on what you're trying to drive it with. The coil driver we utilize is very specialized for rapid scan, and if you're using a resonated circuit, which we are, you can push your scan width fairly far. It also depends a little bit on frequency. The faster you scan, the more limited you become in how wide you can go. So for the typical scan frequencies we use, which tend to be anywhere from about 2 kilohertz up to about 40 kilohertz, we can usually pretty routinely get up to about 6 millitesla. At slower frequencies we can get all the way up to 8. However, I know that other labs, such as the Setlet lab at is he West Virginia or just
West Virginia?
West Virginia. They use an audio amplifier to drive their scan coils, and I don't know if they utilize a resonant circuit or not, but we've tried using an audio amplifier as well, and it's not able to get quite up to the same scan widths as the coil driver is, but it can get pretty close.
Thanks.
Mhm.
So in your N15 imaging spectrum, did you focus only one peak or did you go for the full scan?
For the imaging?
Yeah. No, I mean, for the
I'm
rabbit
so-
scan. For the rabbit scan.
No, we can take full spectra with rapid scan. So one of the early spectra that I showed, actually, let me see where. Oh, my chat's in the way. Where did it go? This one. Both of these spectra were taken with rapid scan, and so this one is, I want to say this one was 6 millitesla wide. This one is 1.5 millitesla wide.
Got it. Thank you.
Mm-hmm.
Yuji, you want to ask your question?
Hi, Lucas.
Hello.
Thanks for the very nice talk. I have a question about this 2D mapping results you show. Maybe it's the second page from the last.
Yep.
I didn't quite follow here. How did you arrange the sample and how that? What is the
sorry.
coordinates
Yeah.
of the point?
I tried to get a better data display, but for some reason I couldn't get my computer to export it properly, so I had to stick with the
Okay.
this sort of image, which is less intuitive, and I apologize for that. Effectively, the resonator that we have is a surface coil. As I have it diagrammed down here at the bottom, the yellow is the supportive material of the resonator, and the red lines here are sort of like if you were to take a cross section of it, this is where the resonator coil would be, and then just sitting right on top of that. So this is our B1 direction right here. Sitting right on top of that are these microslides with there's 4 of them. The bottom one contains our 0.4 millimolar CTPO sample. Where'd my mouse go? There you are. Our top one also contains a 0.4 millimeter CTPO sample, and the middle 2 are just empty, just to provide some significant spacing in between. What we were doing with the spacing was basically trying to see how deep could the surface coil probe. Does that clarify it? Okay.
Yeah. So how large is the coil itself? Like,
Yeah,
is it
the
a
coil
planar
itself.
coil?
Yeah, the coil itself is 1 centimeter in diameter.
Okay. Okay. Yeah. Thank you.
Can you show your spectral slice on the next slide?
Oh, yep.
Do you have any, have you investigated and have you come up with any explanation as to why the intensity goes negative where the peaks are?
Yeah, I know that is an artifact of the way the reconstruction works. I don't know the math well enough to be able to give you a concise answer beyond that. I know that's kind of hand wavy, but in the time I've been doing imaging in the Eaton lab, I have never taken a spectrum that doesn't possess those dips. It kind of almost makes it look like an upside down dispersion signal, but no, that's an artifact of the way the reconstruction works.
Okay, interesting. Yeah, it caught my eye as it looks somewhat like the derivative of dispersion. Is the line width comparable to an absorption spectrum?
Usually when I do these sorts of tests, and in hindsight, it might have been a good idea to show it here. I will overlay this on top of the a non-imaging spectrum of the same sample to sort of qualify how well the reconstruction worked. And usually the line width is very well preserved,
Okay.
which I guess is sort of the aim of a spectral spatial image, is to preserve line width information.
One would hope, yeah. Any other questions from the audience before we thank Luke again for his talk and close this session? Okay. Chat seems quiet and I don't see any hand raised. So I'll just say thanks again, Luke, for giving us this nice informational talk about imaging. To everyone else, look out for our schedule coming up concerning the fall speaker and presentation schedule. We'll get more information out to you guys about that soon. Thanks everyone for joining.